quantify an actual magnetic moment that I not only believe proves the existence of spin, but actually nails down a tangible property of the spin of a proton, bringing us one step closer to defining this phenomenon. So, what can we say about spin so far? What we know about particles like protons and electrons is that they have an intrinsic polarization from which the closest physical approximation we can relate to that of a spinning sphere. Now, this is only an analogy to macroscopic spinning per se, but it's the most feasible way for us to visualize what's going on. Now, one difference between macroscopic spin and quantum spin is that particles can only be in what we call a spin up or a spin down state. Now, if we're discussing protons, when we place protons in an external magnetic field, their lowest energy state will be to align with that field, or to be spin up. For a proton to be spin down, it must counteract the magnetic field, which requires a higher energy than the previous state. Treating the spin axis as a classical magnetic moment, the difference between the energy levels is given by this relationship, where μn is our known nuclear magneton constant, B naught is our controlled applied external field, and some proportionality constant, which we'll call G. From G, I believe that G will give us a proportionality constant unique to protons, characterizing its spin of the magnetic moment. My intention in this experiment was to irradiate a sample of protons with light of an incoming frequency. Photons with a random frequency would pass straight through the sample, leaving the proton in its given state. When the frequency of the photon matches the exact energy between the spin states, we say that it is resonant with the transition energy. Now, when a resonant photon hits a proton, it undergoes a spin flip. Now, when we apply these photons to a sample, two things we know will happen. The first, absorption, in which the incoming photon is absorbed by the proton, shooting it up to the higher energy level. The second thing that will happen is stimulated emission. And this is where the photon forces the proton back down to the lower energy level, producing a duplicate photon of the exact same energy. Now, this makes it tricky for us to define when the photons are in their resonant frequency, but it's not impossible. As it turns out, at equilibrium, there's a very small difference in the population between spin up and spin down states, leading to a very small absorption of energy. It's this really minuscule energy loss that's what our experiment setup is allowing us to detect. In our setup, we have an electromagnet that's supplying the B naught field across a tube of water, which is 2/3 protons. On the sides of the electromagnet are the modulation coils. The modulation coils supply an oscillating magnetic field that adds to the original B naught field. This is necessary for us to obtain an optimal resonance signal, because if we were to just leave the setup in a constant state of resonance, the thermal effects of constant spin flips would overwhelm the energy which we're trying to detect. So the modulation frequency magnetic field, prevents this from happening. The tube is sitting inside a marginal oscillator, which is providing the photons. This acts as an LC oscillator and functions by producing a third magnetic field, oscillating through a coil and instantly detecting the smallest amount of net photons are absorbed, which is what's going to signify when we've hit resonance. Now, of this whole experiment, we're going to be monitoring the marginal oscillator on the scope. Evenly spaced peaks from the marginal oscillator signifies that the field is passing back and forth between resonance, which signifies that the protons are flipping their spin. So when the photons in the B naught field are such that we're in a state of nuclear magnetic resonance and the proton spins are flipping, we've obtained all the values we need to deduce our G factor proportionality constant. So if all the assumptions that we've made about quantum spins so far are correct, they are correct. Then it should be fairly easy to deduce this proportionality constant. By manipulating the frequency of the incoming photons from the marginal oscillator and finding each corresponding B naught field that achieves resonance, we should find that we have a linear relationship between the frequency of the incoming photons and the incident magnetic fields. Now, the slope of this relationship should enable us to calculate the G factor proportionality constant. So I measured these B fields that achieve resonance at different frequencies and proved that they do in fact linearly correlate to each other, and that the linear relationship depends on the magnetic moment of spin. Using uncertainties we measured in frequencies, I used a least squares fit analysis and deduced the G factor of a proton to be 5.6. In successfully performing this experiment, I concluded that energy is lost at resonant frequencies, demonstrating that protons are flipping their spin alignment. I proved a linear relationship of resonance, which enabled me to measure the G factor proportionality constant of a proton. With these findings, I have proved that spin exists and that spin can be quantified. Thank you.